Let's. Any questions? So we're talking about LDPC codes. So those basically they're linear codes for which the parity check matrix is sparse. So typically there's a bound on the number of ones in each row and the number of ones in each. So in the last class, I introduced what are called DV-DC regular LDPC codes. So it's an LDPC code where every column of the parity check matrix has at most DV ones, and every row of the parity check matrix has at most DC ones. And typically the way you should think about this is that DV and DC are constants independent of n. So n could be maybe 1,000 or 1,000,000 or 10 million, but DV and DC are very small, something like 4 or 5 or at most 10 perhaps. Okay. And the main reason why we're interested in DV, DC regular LDPC codes is because now if DV and DC are constants, then if you look at the factor graph of the LDPC code, then this has a very small number of edges. And the degree of each vertex in the factor graph is very, very small. So in case the LDPC, in case the factor graph is a tree, then we know that we can do exact maximum likelihood bitwise decoding by just running the generalized distributive law. Okay? But unfortunately, such codes are not good. So I will try to do a relaxation. So we'll try to look for those codes for which the factor graph is almost like a tree, in the sense that it does not have any short cycles. Okay, so a cycle is basically any path, any sequence of edges which starts and ends at the same node. So you understand what a cycle is. So by short cycle, I mean something which is a constant. Typically, we'll want to design LDPC codes for which the smallest cycle in the factor graph is at least something like log n. So it turns out you can't make it any larger than log n, because you have to, if you think about it, every time you visit a particular vertex, or if you look at the neighborhood of every particular vertex, you're increasing it by a constant factor. So if you look at any path of size n, of any size log n, the total number of neighbors in some sense is already order n. So the largest small cycle that you can hope for is order log n, and we'll hope that there is some constant times log n. So the shortest cycle is some constant, and it turns out that you can construct such graphs. Okay. So it doesn't. So just because I say DV, DC regular LDPC code, it doesn't mean that all DV, DVC regular LDPC codes have short cycles. Okay. So we'll want to focus on those DV, DC regular LDPC codes for which the shortest cycle grows something like order log n. Okay, but we'll get to that a little later. So for now, at least for the discussion that we want to do now, it doesn't really matter. In fact, right now we won't even assume that it is DV-DC regular. The only assumption that we want to make now is that the degree of each vertex is bounded by some constant. But nevertheless, suppose we wanted to construct a DV-DC regular LDPC code, how would we do it? Right, that's the problem, right? Suppose I wanted to pick a factor graph or basically an LDPC code which is DV-DC regular. I want to pick it randomly. How do I generate such a code? Right? So of course, so one way, as I had mentioned earlier, is you can try to do the following. You take n left vertices, m right vertices, m is equal to n minus k, and then for each left vertex you choose whatever DV neighbors uniformly at random. This process ensures that the left degree is exactly equal to dv, but the right vertex, the right degree in general will be much larger than dc. So it will not be dc. There'll be some which have much smaller neighborhood, much smaller degree. Some of them will have much larger degree, and that is something that we absolutely want to avoid. So one way of constructing such regular graphs, or one way of sampling from the class of regular LDPC codes, is the following. It has different names. So one name is the configuration model. Another name is the standard ensemble of LDPC. It's called the configuration model. So this is a name that comes from graph theory, or something also called the standard ensemble. So in this, what do? So you have the n left vertices and m right vertices. So n is the block length, and say m is the number of parity checks. Correct? Now let us pick some particular number. Okay, suppose I want to construct a 2-4 regular LDPC code. So remember, I can't choose dv and dc arbitrarily. I must satisfy the property that n times dv is equal to m times, and in this case I can do it, right? So because so dv is equal to 2, dc is equal to 4. So 2 times 4 is equal to 4 times. Okay, so maybe this is not a very good thing. Let me increase, perhaps let me increase this is n. Okay, so I have 6 left vertices and 3 right vertices. So what do? So I want to ensure that each left vertex has degree 2 and each right vertex has degree 4, right? What we do is the following. So we artificially introduce dv sockets for each variable node. So you'll get to see what exactly I mean by a socket. So I'll draw maybe 2 points for each variable node. So each socket in some sense represents one of the edges which is going to go out from the left, the variable. Now correspondingly, I'll introduce DC many sockets for each right vertex. That's 1, 4, 2, 3, 4. So now the number of sockets on the left is exactly equal to the number of sockets on the right. Correct? Because ndv is equal to mdc. So what do I do now? Since the sockets is exactly the same, I'll map this in a one-to-one fashion. So basically what I'll do is I'll pick a random permutation of ndv. So you can label these sockets as 1, 2, 3 up to n times dv. I'll take a random permutation of this. There are standard ways of sampling random permutations. So that will correspond to some particular permutation. So it's basically a bijection. So you pick a random permutation, and the sockets, basically I merge all of the sockets together for each variable. So right now what has happened is that these two sockets go to sockets for check node number 1. So in other words, there are two edges. These correspond to parallel edges. Not a good thing, but anyway, these correspond to parallel edges. So let us take variable node number 2. This goes to check node 2, and another goes to check node 2. The other goes to third variable node. There's one which goes to check node 1. The second goes to check node. The fourth variable node, one goes to check node 1. The second goes to check node 3. The fifth one, there's one which goes to check node 2. Second goes to the same happens for. So this is one particular realization of a regular DV-DC regular LDPC code which is sampled from the configuration mode. It doesn't exactly ensure that the degrees are DV and DC, because in this, for example, in this case, there are parallel edges. But if DV and DC are very small and N is very, very large, then it is the probability that there will be parallel edges is actually very small. And in any case, what this definitely guarantees is that every vertex on the left has degree at most DV, and every vertex on the right has degree at most DC. Because each vertex has exactly, so every right vertex has exactly DC sockets. So there can't be any more than DC edges incoming on one particular right vertex. Similarly, every left vertex has exactly DV sockets. So at most DV edges can be incident on this. The reason why this can be less than DV is when you have parallel edges. Basically what you should do is you should replace this with a single edge. Yes. Right. So since the degrees are at most DV and DC, the complexity is not any larger. So this gives an upper bound on the complexity of any graph which is sampled according to this particular technique. Complexity can only be smaller. But the only disadvantage is that for some graphs, they may not perform. If you run let's say the belief propagation algorithm, you may get a large probability of error. But the complexity is never going to be high. So now that we've seen how to sample from, let's say, DV-DC regular LDPC code, and we've seen what the belief propagation algorithm is, what the steps are. Now it turns out that for binary LDPC codes, the steps or the message passing rules, the message update rules can be simplified significantly. So originally in the GDL or the belief propagation algorithm, as I had introduced previously, you have to transmit vectors. Right? Every message is basically going to be a binary vector or binary LDPC code. But it turns out that this can be simplified. You don't necessarily have to transmit vectors. It suffices to just transmit numbers. So along every edge, all you have to do is just update one real number and transmit. So let's again quickly recall the message, what messages are and what message update rules are. So recall that the message variable node so the message update rule was the following. Suppose you have a vertex v, a variable node v, so it has a bunch of check nodes as neighbors. Now just to simplify notation, I label these check nodes as 1, 2, 3 up to dv. Or maybe let me just keep it d. Again, there'll be a lot of notation, so I just want to simplify things. And suppose I want to compute the message from variable node v to check node number d. So I have a bunch of incoming messages. So this is mu, I'll call these 1, call this C1, I'll call this C2, this C d minus 1, I'll just call this C. So I want to find the message from B to C. This is going to be a vector, a binary vector. So for each x in 0 and 1, the message is the following. You basically take the product of all the incoming messages, and that is going to be the outgoing message. This is product I equal to 1 to d minus 1 of mu I d x. So for x equal to 0, you basically take all the incoming messages. And for x equal to 1, again, you take all the incoming messages evaluated at x equal to 1. Right? Now this is basically a vector, but we'll try to simplify this somewhat. What do we do? So let me take the ratio of these two equations. So I'll call R B to C the mu V to C of 0 divided by mu V to C of 1. Right? And this is the ratio of these two products, which is basically the same as product I equal to 1 to d minus 1 of mu ci by ci to v of 0 by mu ci to v of 1, which is basically r vi to c. So this is 0 divided by mu v. But each of these is just r vi to c. So this is product I equal to 1 d minus 1 . So now instead of multiplying 2 times d minus 1 many numbers, I just have to multiply d minus 1 number. That greatly simplifies things. In fact, we'll make so this is basically a reparameterization. At these messages, I am reparameterizing this using R V to C. I'll do another reparameterization called LDPC. v to c as log to base e of r v to c. So it's going to be log of mu v to c of 0 by mu v to c of 1. Now this is very similar to the log likelihood ratio. So one way of interpreting these messages is that these are beliefs that the variable node v is actually equal to 0. So the x corresponding to the variable node v is actually equal to 0. And similarly, mu v to c is basically the belief or in some representation or representative of the probability that xv is equal to 1. That is one way of thinking about it. It's not exactly the probability, but it is the belief that v has that it is equal to 0 or it is equal to 1. So that is the way you should think about these. Think of these as beliefs. But these are not any beliefs. These are beliefs based on something. Right? So remember that each message is obtained by taking inputs from all of its other neighbors. Right? So in some sense, this is not so this belief, so each belief that it is transmitting from v to c is independent of what c thinks about v. Right? In some, you should think about it. So one way to interpret this is you're collecting, gathering together all the information that C1 has about V, C2 has about V, and CD-1 has about V, but not what C has about V. And you're telling C that according to these people, xv should be equal to 0 with some, let's say, probability or some belief, and xv is equal to 1 with this particular belief. That is why we can sort of interpret this something like a log likelihood ratio. So log rv to c is something like the log likelihood ratio of what xv should be. Right? And now the update rule becomes the following. So it is log of summation I going from 1 to d minus 1 of rvi to c, which is basically the sum of log of rvi to c, but log rvi to c is lvi to c. So this is just summation I equal to 1 to d minus 1 L. So now we've simplified the message update rule even further. So originally we had to multiply 2d minus 2 many numbers, but now all we have to do is add d minus 1 numbers together. That's a further lowering of the complexity. And the reason why this becomes so important and why we are so focused on the number of operations is because these LDPC codes are going to be implemented on chip. They're not going to be implemented on some kind of computers. So typically they're going to go into devices which have very low power, and you want processing to be very, very fast. So that's why even a single multiplication, saving even a few multiplications per sort of unit time makes a big difference. It corresponds to huge savings in power. Okay, so now let's see what the message update rules are for the check node. So once again, let's assume that these variable nodes are labeled 1, 2, 3 up to d minus 1. And this is check node C, variable node V. So again, I'm using an abuse of notation because this D is going to be different from the other D, but just to make sure that the messages are in a form so that I don't have too many subscripts, superscripts, and so on, I'm just keeping this D. But this D is not the same as the D I had previously. So what is a message update at the check node? The check node, we had the following update rule. So the message from C to V X. So you basically take the product of all incoming messages equal to 1 to D minus 1 mu X to D minus 1 times the indicator. So the local function is basically the indicator that all of these xi sum to 0, so the XOR equal to 0. X here summation a equal to 1 d x a to 0. So this is the message update at the check node. I'm going to write this in a slightly different way. In fact, we're going to reparameterize even the x. So instead of viewing these as elements from 0 and 1, we will basically do the VPSK mapping. We'll map 0 to +1 and 1 to -1. So basically 0 is going to be mapped to +1 and 1 is going to be mapped to -1. Okay. There's a reason. So we'll see that the message update, the messages, or the simplification of the message update rules becomes much easier if we do this particular reparameter. Okay. So now the nice thing is what happens to summation I equal to 1 to whatever d xi. So in the 0, 1 world, the summation, or basically it's the XOR, right? What does this become when you map these to +1 and -1? Yeah. So let's think about it. So 0 XOR 0, 0 XOR 1, 1 XOR 0, and 1 XOR 1. These are the possible combinations, right? So now we've mapped 0 to +1 and 1 to -1. Okay, so 0 XOR 0, as we know, is 0. This is equal to 1. This is equal to 1, and this is equal to 0. So if you map this to +1 -1, then you get a table which looks something like this, right? So you have 1 1, 1 -1, -1 1, -1 -1. Right? So 1 and 1, this pair gets mapped to 1. This gets mapped to -1. This gets mapped to 1. This gets mapped to 1. So in this case, for this particular table, this mapping, this truth table essentially corresponds to the truth table of XOR operation. So what do you think this particular truth table corresponds to? Yeah, it's just product, right? So it's basically, so that's a nice feature of this particular mapping. XOR is basically the same as product. So this becomes product I equal to 1 to d of xi, if each xi is +1 or -1. Right? So I can rewrite this as in the following way. So the message from the check node to the variable node evaluated at x equal to +1 or -1. This is equal to the summation overall x1 d 1 -1 d indicator that the product I equal to 1 to right? So this should be equal to 1, correct? Times the product of all messages. E minus 1 new C xi. So this is the message update rule at right. So this is such that x t should be equal to x, right? If you're evaluating this message at right? So now you fixed one of the elements to be equal to x, right? So the dth element should be equal to x because you want to find the message at x equal to 0 or x equal to 1. Right? So greatly. So we have product I equal to 1 d I should be equal to 1, right? Out of which one of these elements is equal to x, correct? The dth element is equal to x. So this is same as x times product I equal to 1 to d minus 1 xi is equal to 1, right? Basically we want to sum over all possible x1 x2 x3 up to xd minus 1 such that this product is exactly equal to 1, right? Because this basically this parity check has to be satisfied. You only want to sum over those configurations, those xj's for which the parity check is satisfied, right? But what is this the same as? So can I say that this is the same as product I equal to 1 to d minus 1 xi is equal to x? Yeah. So up to here is fine, right? So I'm claiming that this is the same as this product being equal to x. No, actually it should have been 1 by x, right? But what values does x take? 1 and minus 1. But so 1 by 1 is equal to 1 and 1 by minus 1 is equal to minus. So because we're considering only the binary field, we can use this property that 1 by x is equal to x. So another way of writing this particular update rule is mu c to v x is equal to the summation over all possible x1 up to x d minus 1 such that the product I equal to 1 to d minus 1 xi is equal to x. So if I only sum over these particular elements, then the indicator function is always equal to 1 times the product j equal to 1 to d minus 1 messages from the xj. So this is basically the update rule. Now again, remember we want to reparameterize everything. So this is for x equal to 0 and x equal to 1, we have this particular update rule. Now, so let us look at our C to V. We basically want to bring this mu C to V to an R C to V. Right? So R C to V would basically be the following. Plus 1. So both the numerator and the denominator look very, very similar. The only difference is that the numerator, you're summing over all configurations for which the product of all the xi's is equal to plus 1. Whereas in the denominator, you're summing over all possible configurations for which the product of the xi's is equal to minus 1. Okay. So now I'm going to perform some more steps. Okay. So firstly, I want to somehow bring the right hand side to also be of the form Rvj to C. So what I'll do is I'll multiply and divide both the numerator and the denominator by product j equal to 1 to d minus 1 mu Vj to C of minus 1. Okay, not xj. Vj C of minus 1. So I can't really multiply and divide by mu Vj to C of xj, and that is because the configurations that I'm taking on the numerator could be different from the configurations I'm taking in the denominator. So I'll multiply and divide by mu Vj to C of minus 1, product over all j. Okay. Now let's think about each of these terms. Right? When xj is equal to plus 1, this is exactly equal to R C to V. When xj equal to minus 1, this particular quantity is what? It cancels out. So it's equal to 1. Right? So equal to 1 up x d minus 1, that the product I 1 d minus 1. So I want to write this in terms of R Vj to C. Right? But not all R Vj to C's are present here, right? Only some of them. So I'll write it in the following way, and you tell me if this is correct or not. So R Vj C to the power 1 plus xj by 2. Okay, so xj is either plus 1 or minus 1. When xj is equal to plus 1, this becomes 1 plus 1 by 2, which is R Vj to C. And that is exactly what we had over here, right? So when xj equal to plus 1, this is mu Vj to C of plus 1 by mu Vj to C of minus 1, which is R Vj to C. When xj equal to minus 1, the exponent is 0, and that's exactly the same as what we wanted because it should cancel. Okay, so this is one step. Now the next step is something a little more surprising. So now the problem here, okay, so now these computations are fairly simple. But now the problem is that I'm not summing over all possible x1 up to xd minus 1, right? Because now I have to check whether x1 to xd minus 1 is such that the product is equal to 1, right? And that's a computationally complex task. So now here's sort of the big simplification. So this is equal to the product I equal to 1 to d minus 1 of r bj to c plus 1 plus product I equal to 1 to d minus 1 bj to c minus 1 divided by product d minus 1 a to c 1 minus product I equal to 1 bj to c. Okay. Now this requires some argument, because all of a sudden, now this seemed to be a very complicated expression, but now all of a sudden I seem to have make this much simpler looking, right? Because now it's just product I equal to 1 to d minus 1. There's no real checking involved whether it's this particular configuration. So let's see why that is the case. So let's think about which elements were kind of multiplying, right? So but maybe before that, let us look at this particular quantity. So product I equal to 1 up to d minus 1 of vj to c plus, or maybe forget about r, vj to c and everything else. Let me just say alpha I. Yes, so alpha I plus 1 for some alpha 1, alpha 2 up to alpha d minus 1. Okay, so I have this particular quantity. What does it look like? So it's equal to 1 plus alpha 1 plus alpha 2 on up to alpha t minus 1 plus alpha 1 alpha 2 plus alpha 1 alpha 3 and so on, all possible pairs, and then all possible triples and so on, it all the way up to product I equal to 1 alpha I. Right? So for example, if I took, let's say, d minus 1 equal to 3, then this would be alpha 1 plus 1 times alpha plus 1 times alpha 1 plus alpha 1 plus alpha 2 3 plus alpha 1 alpha 2 plus alpha 1 alpha 3 plus 3 plus alpha 1 alpha. Okay, so now what happens to the other term? So I have alpha 1, let's say I have alpha 1 minus 1 times alpha 2 minus 1 times alpha 3 minus 1. What would this be equal to? So in this, you have exactly the same terms, but the signs could be different. So now let's take alpha 1, let's take the 1 terms. I have minus 1 into minus 1 into minus 1, which is minus 1. And then I have alpha 1 into minus 1 into minus. 2, 3. Then, sorry, what is it? Are you sure it's plus alpha 1, alpha 2? It is alpha 1 into alpha 2 into minus 1, right? So it's minus alpha 1, alpha 2, and then minus 1 into alpha 2 into alpha 3, minus alpha 3, then alpha 1 into minus 1 into alpha 3 is 1, 3, and then I have alpha 1 into alpha 2, 2, alpha 3, right? All right. So now if I sum these two, what do I get? So I get 2 times alpha 1 plus alpha 2, correct? Okay. Now, suppose I had to, let me go back to what I basically wanted, right? So what did I want? I wanted to multiply only those terms for which the product is equal to 1, right? And basically, so this means that, okay, so again, let's look at d minus 1 equal to 3, right? I want those xi's for which x1, x2, x3 is equal to plus 1, right? So if x1, x2, x3 should be equal to plus 1, then an even number of the xi's should be equal to minus 1, correct? That has to be the case, right? And I'm only keeping the plus 1 elements intact, right, over here, right? So now, so which terms would that basically correspond to? Correct. So it will be alpha 1, alpha 2, alpha 3, and alpha 1, alpha 2, alpha. So in this case, basically x2 and x3 are equal to minus 1. For this particular term, you have x1 and x3 equal to minus 1. And in this term, none of them are equal to minus 1. So basically what we want is the following. We want summation over all possible x to d minus 1, that product I equal to 1 of product j equal to 1, 1 alpha j whole raised to 1 plus j divided by 2. Correct? So in this, some of the alpha j's are going to be present and some of the alpha j's are going to be not present, right? So in each of these, the number of j's for which alpha j is not present should be even, correct? Even. Let's think about it. Now, can we get a general formula for this particular expression? Product I equal to 1 to d minus 1 of alpha I plus 1. I can write it in the following manner, right? So it is the product over all x1 to xg minus 1 in say 1 comma minus 1, right? So a 1 implies that alpha I is sort of selected. So what does each term look like? Each term is a product of alpha I and 1, right? So basically you have alpha 1 plus 1 times alpha 2 plus 1 and so on. Now from each of these terms, you either pick alpha I or you pick, right? So for example, in this, right? So this term was obtained by picking alpha 1, minus 1 and then minus 1. So from each of these, you have to pick one of these two terms. And let's say that plus 1 corresponds to picking alpha I and minus 1 corresponds to picking. So I want to write this as A equal to 1 D minus 1 alpha A raised to something times 1 raised to something. Right? So if xi is equal to 1, I should pick alpha j. If xi equal to minus 1, I should pick 1. How do you think you could write this? Okay, so let's say I put 1 plus xj by 2. Okay, what about this? 1 raised to 1 minus xj divided by 2, right? That is fine. Anyway, 1 raised to anything is just going to give me 1, so it doesn't matter. But this is still a useful exercise. Okay. Now, what about product I equal to 1 to d minus 1 of alpha I minus 1? So once again, this is summation over all x1 up to xd minus 1 are in 1 or minus 1. Product j equal to 1 of alpha j whole raised to 1 plus j by 2 times minus 1 raised to 1 minus xj by 2. Right? Okay. So now let's add these two up. I add these two up, then basically I get summation over all possible x1 up to xd minus 1 of product j equal to 1 to d minus 1 alpha j whole raised to 1 plus xj by 2 times product j equal to 1 to d minus 1, or the way to put it is basically 1 plus product j equal to 1 to d minus 1 of minus 1 raised to 1 minus xj whole divided by 2. Correct? So this would correspond to this particular term, whereas this times this would correspond to this particular. Now what can we say about this? So this whole quantity is either plus 1 or minus 1, right? So this whole thing is plus 2 or 0, right? When is it equal to plus 2 and when is it equal to 0? So how many of the xj's can be -1 for it to be equal to +2? Put it a little. So remember, you're multiplying a bunch of -1s, right? Right. So you want this product to be equal to +1, right? For this to happen. Now, if this product has to be equal to +1, how many -1s can you have? So remember, this product is either -1 or equal to +1, right? Depending on xj. Right? How many of these terms can be -1? Even number, odd number? So if an odd number of these are equal to -1, correct, it will be -1. If this is equal to, if this whole quantity is -1, what is the sum equal to? Sum is equal to, right? So fine, let us take this. So if an odd number of these are equal to -1, then it is equal to 0, right? But when can an odd number of these be equal to -1? What can you say about the xj's? So what should xj be for this to be equal to -1? Correct. So correct. If what happens? If one of the xj's is 1, right? But you're multiplying a bunch of xj's. In fact, okay, so let me maybe simplify this a little bit. So -1 whole raised to 1 minus xj by 2, right? So this is equal to +1 if xj equal to it's equal to +1 when xj equal to what? So xj is +1 or -1. Let's take one of these terms, right? When xj equal to 1, this whole quantity equal to +1. When xj equal to -1, this whole quantity equal to -1. So basically I can just replace this with xj, right? Do you agree? Okay. So that kind of simplifies things. So this is 1 plus product j equal to k minus 1 of xj, right? So it's equal to +2 if product j equal to 1 to d minus 1 of xj equal to +1, equal to 0 if product j equal to d minus 1 xj equal to -1, correct? Which is exactly what we wanted in the numerator, right? So remember, so we were summing over all xj's for which the product is equal to +1 of this quantity, which is exactly what we have, except we have a scaling multiplicative factor of +2, right? The same holds for the denominator, right? The denominator is basically the same. So this quantity is basically going to be 2 times this quantity, right? And this quantity is going to be 2 times this quantity. So 2 and 2 get cancelled, and therefore you have this quantity equal to this particular quantity. That's a big simplification that we did now. Okay, but now I want to do another reparameterization, right? I want to so this is sort of in the likelihood ratio format. I want to bring it to the log likelihood ratio. So this is our C to B. Okay. Now this in itself does not seem to be very simple to look at. Right? So I'll do the following. So So these terms are the same both in the numerator and the denominator. So I'll divide both the numerator and the denominator by this particular product. I get 1 plus product a equal to 1 to p minus 1 of r pj to c 1 divided by pj to c plus 1 whole divided by 1 minus product j equal to 1 to p minus 1 pj to c 1 divided by pj to c plus 1. Okay, that's good. Now I want to replace this with the L messages, right? So we originally had the mu messages, and then the R messages were basically the ratio of mu of 0 divided by mu of 1, or mu of plus 1 by mu of minus 1. And now I want to take L to be log of R. So see, log of this is equal to L V to C, or R V to C is basically equal to E raised to L V to C. Right? Let me write it in this particular form. So E raised to L C to V is equal to 1 plus, it's 1 plus product E raised to LV to C minus 1 by E raised to LV to C 1 divided by the same, this product J equal to 1 P minus 1 E raised to L J to C by E raised to J to C plus 1 whole divided by 1 minus product J equal to 1 to D minus 1 E raised to L J to C 1 divided by E raised to L J to C we have e raised to x minus 1 by e raised to x minus, sorry, e raised to x minus 1 by e raised to x plus 1. Does this look familiar to some function you've seen before? E raised to x divided by e raised to x plus 1, or you want it in a slightly simpler fashion, suppose I multiply and divide both the numerator and denominator, sorry, I divide both the numerator and the denominator by e raised to x by 2. I get e raised to x by 2 minus e raised to minus by 2 divided by e raised to x by 2 plus sinusoid. So if it were e raised to ix by 2 minus e raised to minus ix by 2, where I is the square root of unity, square root of minus 1 divided by e raised to ix by 2 plus e raised to minus ix by 2, then that would be tan x by 2. But what is this equal to? This tan hyperbolic, tan h of x by 2. This is 1 plus product of tan h by 2 by 1 minus product tan h exponent. E raised to L P is equal to 1 plus product J equal to 1 tan H LVJ to C by 2 divided by 1 minus product J equal to 1 to T minus 1 tan H of L Pj to C. Okay, so let's look at the right hand side now. Right hand side is of the form 1 plus alpha by 1 minus alpha. Call the left hand side beta. Okay. So what is alpha going to be equal to in terms of beta? Yeah, in terms of beta, as a function of beta. Correct. So it is beta minus 1 divided by beta plus 1. Okay, so now our alpha is basically the product of all of these. This product J equal to 1 to D minus 1 tan H of L 2. This is equal to beta minus 1 by beta plus 1, where beta is basically equal to this, right? E raised to L B minus 1 divided by E raised to L e to V plus 1. But what is this equal to? Correct. So it is tan H of LCB divided by. So now if I want to compute tan H LC to V, I just have to do tan H inverse. L C to V, I can write this as 2 times tan H inverse of product J equal to 1 to T minus 1 tan H of L Pj to C2, right? Correct. So now this simplifies things greatly, right? So earlier I had to sum over some specific configurations, multiply messages, and so on. Right now, all I need to do is I get a bunch of real numbers, I compute tan h of each of those numbers by 2, multiply them, take tan h inverse, multiply by 2, and that's the outgoing message. That's very, very simple. So in fact, the belief propagation algorithm for LDPC codes can be summarized in the following way. Right? So first you initialize. Right? So for each variable node, you get some p y given x. Right? So initially you set L vi from the ith from basically from xi, the vertex corresponding, right, to cj at time t equal to 0 to be equal to log I given 0 by I given 1. Okay, so these are going to be the initial messages. So each variable node is basically going to just broadcast this to all possible chains. Then you keep running the following. You do the following until convergence. So from the jth check node to the ith variable node t equal to 1, 2, and so on up to convergence. So at the check node, you basically multiply these a v, which are neighbors of cj, but I exclude tan h to take h inverse and multiply by. So this is what I do at each check node, and then at each variable node, this is sent at time -1 L I J T is basically just the sum overall C, which are neighbors of I, but I'm excluding J, L, so you keep doing this until it converges, and in the end you get some messages. Okay, but now you need to, of course, do a final estimate. So what is the final estimate going to be? So the final estimate is what we'll call the belief, right? Or in other words, the log of the beliefs. So I'll call this LVI, and this is obtained by summing all the neighbors. I sum all the incoming messages, okay, to get this quantity LVI, right? So this is sort of the log likelihood ratio, right? So declare xi hat be equal to 0 if LVI is greater than 0 and 1 if I is less than or equal. Basically, if the log likelihood ratio is greater than 0, then you declare it as 0. Otherwise, you declare it to be 1. So for a binary LDPC code, basically all you have to do is run these steps. So given any discrete memoryless channel, you can run this. And in fact, it doesn't even have to be the alphabet. The output alphabet does not even have to be finite. If the output alphabet is, say, the reals, for example, if it's a binary input AWGN channel, you can still run this. Instead of taking PYI given 0 by PYI given 1, you just do f of yi given 0 by f of yi given 1, where there are the conditional PDFs. For example, for a binary input AWGN channel, you can still run this BP algorithm. The only constraint is that the inputs are binary. You either transmit 0 or you transmit -. Right? And this is exactly what is being implemented in chips today. So there are further simplifications made. For example, you restrict yourself to maybe more specialized parity check matrices and so on, so that you don't have to evaluate all of these for all nodes. But in general, this is already fairly good enough. Because again, what do you have to do in each step? You just have to multiply a bunch of numbers. Again, the number of multiplications, this number of multiplications is a constant, right? And you do this for linear number of elements. So constant number of multiplications. Again, here you're doing a constant number of additions. You run this for a certain number of steps. So in each iteration or each step, you only incur linear complexity, right? Because the overall complexity of this is constant. Overall complexity of this is constant. Have n vertices to do this for. So overall, in each iteration, overall complexity is just linear. You run it for how many ever iterations you want. So overall complexity, computational complexity, is basically linear n times the number of iterations. And it turns out that if you want this to perform well, then the number of iterations can't be kept just a constant. That is not enough to get a good estimate. Right? So at least theoretically speaking, the number of iterations is typically chosen to be growing with log n. So the overall complexity is n log n, which is still fairly good. Right? And of course, these are all theoretical estimates, but in fact, in practice, you get much better results. Right? So basically, for block lengths of, let's say, 1,000 or so, 1,000 or 10,000, in many cases, you just run belief propagation for maybe 100 iterations, maximum number of iterations to be equal to 100. But sometimes you can terminate it even faster. For example, if you see that the messages in these steps, if you see that from the previous iteration to the next iteration, the messages have not changed much, then you don't need to run any further. You just stop, you just skip from this particular iteration and then find your final estimate. And then there are, of course, a number of other numerical improvements that you can make to improve complexity and so on. Right? So, any questions? So let's maybe stop here. It's a good place to stop. So now, just to summarize, what we've seen is we know how to construct random regular LDPC codes. We also know how, for a general discrete memoryless channel, how we can perform belief propagation decoding over a given LDPC code. Now, the problem, as it turns out, is that if you take a regular LDPC code, then it does not achieve capacity. For example, in the previous class, I had just shown a simulation of belief propagation for the binary erasure channel. And the best rates that it could achieve was somewhere less than capacity. The capacity turned out to be 0.5, but then you could get low error probability only for at capacity, although the rate was half, it was only for p less than or equal to 0.4 or so that we could get good performance. Right? So it turns out that that's a limitation of the code itself. You can't take a regular LDPC code and get to capacity. So for that, we'll need to change things a little bit. Instead of choosing a regular LDPC code, you choose what is called an irregular LDPC, wherein the degree distributions are not fixed. So the degrees are not fixed. So not all vertices have degree equal to 3 or something, but you change the number of vertices which have a certain degree. Maybe you say that half of the vertices are going to have degree 3, and the remaining half of the left vertices are going to have degree 4. Similarly, you do something like that for the right vertices. And that, it turns out, you can choose the degree distribution. Again, the degrees are bounded above by some constant. Complexity is not going to increase significantly. But by introducing this variability, you can now suddenly achieve capacity. And this was a great result way back in 2000 and so. So we'll see what irregular LDPC codes are. The construction is similar to what we've seen before, and decoding rules are exactly as what we have here. But what still remains is, how do we show whether a class of LDPC codes is good or bad? Of course, you can pick a random LDPC code, do simulations, and so on. But is there a way of predicting whether a given degree distribution is going to be good? What is the maximum rate you can achieve for a given probability of error? And suppose now I want to optimize. I want to choose that degree distribution which lets me achieve capacity. How do I do this? That we'll see that in the coming class. Okay, so let's stop here.